All right. Let's talk about some application problems today. And I'd like to give you a gift of a little note sheet that has 3 examples written on it. Okay? Just because they're word problems, and I'd rather not have you spend like time writing down the whole paragraph about the Barnegat Bay Lighthouse and all this stuff. Okay? You might still want a notebook nearby in case some of the pearl of wisdom that needs to be captured can be captured.
Yes, it is.
I think all government.
You win this round.
All right, everyone's getting a note sheet. Can I get a reader, please, for the first one more? All right, listen quietly while the following person reads. Rosie, go.
The angle of depression of a buoy from the top of the Barnegat Bay Lighthouse, 130 feet above the water, is 6 degrees. Find the distance from the base of the lighthouse to the buoy.
Okay, so the first thing we need to do is draw a picture. Please use your art skills. Are you ready? Okay, so we're drawing a lighthouse. Everyone, draw your best lighthouse. All right. Maybe some shading. All right. Maybe some rocky crags that it's sitting up in. Okay. And we need a buoy, too. It's blinking, it's light on. This guy's shining bright. Put a little bird in the sky. All right, here we go. So now we'd like to do some math here. This guy, we're wondering how high. No, we're asking how far away the buoy is, right? I guess is what we're trying to figure out. This is said to be 130 feet. And this is unknown to us right now. We'll assume that's 90 degrees. And here we go. How did I do? Okay. It's a big board. Sorry. Okay. So you also need to understand what we mean by angle of depression. So I'm about to define that for you right now by way of me showing you with my head. Okay, here we go. Are you ready? So here's what angle of depression means. We look out toward the horizon horizontally, just like along this dashed line if you were sitting up in the lighthouse. And then you depress your eyes 6 degrees like this. Right? Does that make sense? So this is 6 degrees is what the problem is telling you. Okay? Does that make sense? You look down 6 degrees, and hey, look, there's a buoy. All right, so not to scale. Please, let's be clear, not to scale. So I think we've marked all the information, and the thing we'd like to know is this distance. You want to give it a name temporarily? X? Okay. Actually, I'd like to call it more like something that's from the Roman alphabet than from the Greek alphabet, because Greek alphabet we usually reserve for angles. All right, just style points. X I like, D for distance would be fine, something like that. Yes. Yeah, always from the horizontal. Yeah.
So if it was tipped over this way, like the angle of depression would be at the bottom.
You'd always be looking down though. So if you're on the ground, angle of depression might not mean much if you're on the ground, right? You can either like looking into the ground. Yeah, usually you're standing above if we're going to think about looking down. I don't know. In another problem, we're going to use the word elevate, angle of elevation, and maybe that'll be what you like. Yeah. All right, so please help me. I have an X. I'd love an equation involving X because I'm an algebra master, and I'd like to solve that equation once you give it to me. But I need you to give me an equation involving X. And maybe it's going to have something tricky about it. Yeah. Oh yeah, maybe we want to have some angles inside this big triangle we drew. That's 84 degrees because they're complementary. Okay. You could also label this angle as, this angle is what?
Parallel lines.
Yeah, someone I hear parallel lines, alternate interior angles I hear someone say. Right? One way or another you can label, please. Thanks guys, let's bring it back together even though I know you're excited. Okay. One way or another you're going to be able to label those angles, and then now let's ask the question again. Can someone please give me an equation, possibly involving a trig function, that has this x in it? Now, you can do that for me?
Yeah.
Okay.
It said tan of 84 equals x over.
Okay, do you see where she's coming at? X over 130 feet, that's the tangent of 84 degrees. That makes, you see what she did? Maybe you had something different. Someone else want to give another, or a couple different options you could write down? Yeah. Tangent 6 equals, oh wait, hold up. You said cosine 6? Cosine 6 degrees equals, careful, I think cosine involves, okay. So tangent of 6 degrees equals 130 over x. Do you like that too? Is that okay? Okay, good. And there are other things you could write down. You could actually write down something involving sine or cosine, but then what would that mean? You'd need to compute. You'd have to express this hypotenuse as the square root of 130 squared minus x squared. Don't want to really go there if I don't have to, and since I don't have to, then I'm not. Okay. So solve one of these equations. I'll do the first one that was given to me by Ananya. I'll solve her equation because she was the first one that gave it to me. But you can solve this one too, equally good. So we get x equals, someone approximate this please on their calculator. 130 times tan 84. Make sure your calculator's in degree mode before you tell me this answer. Make sure your calculator's in degree mode.
So when it's specific, if it's greater than four digits, it's always going to.
Yes, you're getting 1236.867, right? Something like that. So to 3 sig figs, to three sig figs, that's 1240. Right, 1240. Is that okay? 3 sig figs. If you're in IB world, then that's what we do. Okay. Moving smartly along. Reader number 2 is. All right, listen. Reader number 2 is this person over here somewhere. Adele, you want to do it?
I think she volunteered.
Yeah, that's the secret desire to volunteer yourself. Go ahead, Adele.
Here, I'll learn it next.
Go ahead. Listen.
An observer on top of a 100-foot building watches a car approach the building. The person observes the angle of depression of the car change from 22 degrees to 46 degrees. How far does the car travel?
Okay, I'm all about the pictures. Here we go. I don't know what kind of car it is. It's a little shoe car. It's a hatchback. Okay. Yeah, something. Okay, here you are, person on the top observing this happen. Now we want to draw some things here. Again.
Are we accounting for the height of the person?
Yeah, we definitely are. It's actually, the problem meant to say, it's 100 feet to that person's eye. That's what it meant to say, okay? And by angle of depression again, remember we mean we're looking out this way, and then we depress our eyes, and we see the car at 22 degrees. Here we go, right? And then later we depress it. That's a terrible line, sorry. Yeah, whatever. Okay, go with it. No, but thanks for asking. Yeah. No, it's not. Homework 5 is not covered like this one. All right, pretend those are straight lines. So a minute later, whatever it was. All right, do you see the triangle? Triangles, I should say. Right? And what would we like to know? We'd like to know how far the car traveled in the time period between our first and second observation. So let's call that D or something, or the thing we desire. No, the distance between where the car was and where it is now. And then again, we want some equation that involves D, right? But that's a little less obvious this time, huh? Huh?
If you said that the full length was x, then you could find.
All right, let's define the full length to be x because Teo said so.
Then you could say that tangent.
You could say some things. Yeah, so say something.
Tangent 22 would be 100 over x minus no.
Here's 22. Here's 46. All right, so say this time like you mean it.
Say that tangent of 22 degrees would be 100 over x.
Tangent of 22 degrees is equal to 100 over x. I'm with you, okay.
100 over x. And you could also say that tangent of 46 degrees would be 100 over x minus d.
All right, let's just slow down for a second, everybody, and make sure you understand what Teo just said. Do you like what he just said?
Yes.
Stare at it for a second so you do like what he said. Because I think now we can throw away everything in the picture and everything, and we can just look at these two equations and just get our answer. You think? Do it. Let's do it. I mean, right away we know what x is, right? It's 100 over tan 22, isn't it? And over here we know x minus d is equal to 100 over tan 46. So I think that means that x is equal to 100 over. So race me to this here. See if you can get an answer on your calculator before I can. Minus 100, no plus. 100 over tan 22. I'm sorry, I solved for x, that's not what I meant to do. D is the thing we desire. So what is D? Yeah, let me do this slowly. D is equal to x minus 100 over tan 46. So anyone have a approximate value for me here?
We have to do the same thing. No. Yes. Don't trust it.
All right, what'd you get?
151.
151. All right. Someone agree? 151 feet. All right, let's move on. Anyone want to read about Spider-Man? Yes, you do. Go ahead. All right, listen up. Shh.
Spider-Man is crawling up the side of the building. An observer 200 feet away from the bottom of the building records Spider-Man as having a 30-degree elevation, and 23 seconds later having a 40-degree elevation. What is Spider-Man's average velocity during this time?
All right, so here's Spider-Man. And there's Spider-Man. Okay. Here's you observing Spider-Man moving up the wall. So there's a good picture. What do we know? So this is the elevation question here. So elevation means, we haven't defined that yet. It means you look out horizontally and then look up 30 degrees or 40 degrees and you see, there he is. Oh, wait, 40 degrees. There he is. Okay, so we'd like to know, well, what would we like to know? I don't know. This is 30 degrees. This is 40 degrees. This is 200? Yeah. And what would we like to know? I mean, eventually the average velocity during this time period. But what would be helpful in the interim if we could figure out? Yeah. Yeah, so that's this distance here. It kind of feels like the car problem a second ago. So you want to call that, what do you want to call that? You want to call it D again? Okay. You call it H for height or something, or whatever. We'd like to know D. Maybe we give this a name also down here, like, or the whole thing. What would you like to do? You want to call the whole thing X again, or which should you like? I do went with. You want to do the whole thing again? Do you like that? Okay. We'll call the whole thing X again. We'll keep with the notation from the last one. That's fine. And then again, write down some true statement that involves X or D or both or whatever, right? And solve. Did you say what I said here? I don't know. I mean, you can use a different approach, but. So, figure it out here. I don't know. I'm trying to figure out what D is in the end.
Yeah, I got it.
So, what distance did you get for D? Anyone out there? 52.3 feet. All right, and then how do we compute the average velocity? Well, let's just assume that he was going at the same velocity. That's what average velocity means. He went that far in 23 seconds, so what's his average velocity?
2.28.
It's his distance divided by his time, right? So that comes out to, what did you say, 2.2? 2.2? 8? 2.27? I don't know which.
It's rounded to 2.28.
Yeah, is it close to 2.28?
Yeah.
Let's go with that then. Feet per second. Okay. All right. Great. All right, with the last 2 minutes, we still have some time. I want to warn you that tonight we have some problems in the homework from the book on the law of sines as well. Now, maybe you've thought about this before, maybe not, but let me just throw it up here. It's new, it's brand new maybe, but it's very easy to use. Now, there it is. This is true, listen, this is true for any triangle ABC is what this says up here, not just a right triangle. That's new. Everything we've been doing today has involved right triangles. But this involves any triangle. Here's an arbitrary triangle I drew called ABC. And I challenge you to prove it. It's pretty quick, actually, easy result. Using this picture, I think you could prove it, at least this first part. Forget about the sine C over C. But this is saying that the sine of every angle in a triangle divided by the opposite side is the same, regardless of which angle and side pair you're looking at. Okay? It's true for any triangle, not just a right triangle. This will help us solve a host of different problems. Let me show you a kind of problem that you can solve, but the bell's going to ring soon, so we probably won't solve it all the way through, but we can at least look at it. Do you know how to label a triangle? A, B, C, and then opposite sides are little a, little b, little c. Opposite the big angles A, B, and C, right? Big B, little b. What begins with B? Okay. I promise I'll go back in a second here. Some of the problems will ask you to do the following. Solve the triangle. Anytime they ask for you to solve the triangle, they're basically asking you, give me all the angles and all the side lengths, right? We're giving you these. Right away you can write down angle S, can't you? And then, using the things we just saw, we see sine of 36, that's sine of Q, divided by 8, that's Q. That's equal to sine of R over little r. We don't know what little r is, but in a second we will, won't we?
Is homework 5 due tomorrow or due Monday?
I won't check it till Monday. Homework 5 is due on Monday. What's that? All right. No.